I have here a paper that completely revolutionized our understanding of light and of electromagnetic radiation in general, and we can even say of microscopic processes as a whole. This paper, originally published in the journal Annalen der Physik, is from one of the greatest physicists of all time. Probably guessed it, his name is Max Planck. And the title of this paper is Über das Gesetz der Energieverteilung im Normalspektrum. So I would like us to go through some of the main ideas that Planck introduces in this paper, and really just to contemplate, the physics, but also how when you use the appropriate mathematical tools, you can really describe natural phenomena and establish theories or laws that can change our understanding of the natural world. So, to set on the stage, let's maybe give an overview of the big problem that physicists were facing at the time. So, there was this object, an idealized body known as a black body, and essentially it's one that can absorb radiation, that can absorb energy, and in turn emit radiations in the electromagnetic spectrum. The point is, at that time, physicists knew how a black body should behave experimentally. Like, there were experiments that could be done to understand the emissions of a black body, if you want, as a whole, its behavior. A black body emits electromagnetic radiation in a very specific way, depending on its temperature. Theoretically, nobody could explain it correctly. We had at the time two laws that seek to describe the behavior of a black body. There was on one side Wien's law, which worked well for high frequencies, but then failed at low frequencies. And on the other side, we had Jean's law, which was kind of based on classical physics, and it worked well for low frequencies, but then at high frequencies, it predicted that the amount of energy that would be released would be infinite. So uh, this phenomenon was nicknamed the ultraviolet catastrophe. To summarize, if you want, classical physics could not explain the real black body radiation spectrum that we could observe experimentally. Then came Max Planck, which had already spent years trying to resolve this issue. He initially tried to tweak existing theories to fit the experimental data, but then nothing worked. And Max Planck was kind of an adept of classical thermodynamics, but then he hated statistical methods like Boltzmann ideas of entropy and so on. So he found himself into a situation where he was forced to use what was left, and what was left was Boltzmann statistical methods. He later called this, I think, an act of desperation. So Planck's main idea that he introduces in this paper is that he imagines a black body as containing infinitely many resonators, and each vibrates at a certain frequency. Then, like, these resonators can exchange energy with the electromagnetic field, and then he can calculate the total energy of these resonators. Like, if you have n resonators, then the total energy Un is just n times the energy of one resonator. Same goes for the entropy. You probably noticed that this is Boltzmann entropy, S equals K log W. Like, if you have a certain number of states, W, and you want to calculate the entropy associated to the states, you need to take the logarithm and then you multiply by this constant known as the Boltzmann constant. Also, Planck makes use of Stirling's approximation. This is kind of what you use when you're doing statistical physics. If you want to count the number of states of a system, you usually make use of these approximations. And he succeeds to work out a function that is consistent with both Wien's law and James' law. So essentially, he comes up with the fact that the energy density, okay, of electromagnetic radiation can be described as a function that depends on the temperature, the frequency, and the speed of light. Then he introduces this new idea of quantization, which is the fact that the energy of an electromagnetic radiation depends on its frequency nu. Doing that, he then comes up with this law that we know, which is Planck's law, essentially. And then he also computes the value of this constant h. By the way, that constant, he didn't call it Planck's constant. He just called it some fundamental constant of nature. And he computed the value, which is the value that we know today, 6.6 times 10 to the negative 27 SI units. And as you noticed, his constant is very well consistent with Wien's law, and this accurately describes the energy distribution of an electromagnetic radiation at all frequencies. Maybe what's important to note here is that this idea of quantization is not really something that Planck believed was revolutionary. For him, it was just a mathematical trick that he used to match the theory with the experimental observations. But then it's only when Einstein will come, like a few years later, that he's going to use, this energy quantization seriously and then explain the photoelectric effect, which would enable us to understand later on that actually light propagates as quanta of energy. And each quantum, if you want, has an energy given by this expression, which in turn implied that the Planck's constant is maybe even more fundamental than Planck thought himself, because it's really a constant that's linked to the speed of light and just linked to nature itself. And as you probably know, this was the birth of quantum mechanics, because later on these ideas will be incorporated into the broader framework of quantum mechanics, Schrodinger's equation, and so on, to describe microscopic processes and quantum systems. So it's fair, I think, to say that thanks to this paper, uh, we entered into a new era of physics. Okay, and who knows what's next. So big thanks to Max Planck.